Okay, so this is going to be my first work solution video for linear algebra. So I've been asked to go through practice test question 3, which is to use the Gram-Schmidt process to find an orthonormal basis for the vector space V, which is the span of these two vectors, 2, 0, 1 and 0, minus 1, 1. So I'll just say a few general things first. So the span means that this vector space is the set of all linear combinations of those two vectors. We can see that one is not the multiple of the other, and so therefore they are linearly independent, and therefore they must span a two-dimensional space, which means we will have a two-dimensional vector space. So that means that we're going to end up with, we're going to start with two vectors, and we're going to, our orthonormal basis will also have two vectors, because these two basis vectors are linearly independent. So my method is very slightly different from that given in the work solution. So I'll mention the differences as I go, but basically comes down to the same thing. But I'll mention the differences that I have. So the first thing to do is just to start with some definitions. I'm going to call U1, and I'm going to use the row format for these vectors. So I'm going to write them as row vectors. They're exactly the same thing. So it's just a different way of writing the same thing. I find this notation more convenient because when I'm doing dot products and things, I'm used to writing them in row format, so I'm going to stick to it. And we're going to let U2 be equal to the other vector, 0, minus 1, 1. So with the Gram-Schmidt process, the first step is to choose one of these vectors arbitrarily, and that's going to be the direction of our first basis vector. But we want to make it, for it to be an orthonormal basis, we need it to be a unit vector. And so what we need to do is we will find the magnitude of U1, and that's just equal to the square root of the sum of the squares of the entries. So 2 squared plus 0 squared plus 1 squared. So that's equal to the square root of 5. And so I'm going to straight away write down our unit orthonormal, our unit vector in the same direction as U1. That's going to be called W1. We're going to divide by the magnitude of U1 to ensure that this is a vector in the same direction as U1, which has magnitude 1. And so this is equal to 1 over square root of 5. And then we just write the previous vector, 2, 0, 1. And I'm going to write this is the first vector in our orthonormal basis. And so usually what I'll do is I'll try to stick to the convention that the U's are the initial vectors, V's are potentially a set of orthogonal vectors which I generate from the U's, and the W's will be the orthogonal vectors which are all normalized to have unit length, so that they form an orthonormal basis. Next step is to try to work out what we need to find a vector which is orthogonal. We need to find the component of U2 which is orthogonal to U1. So the way we do that is, this is just an explanation, okay, so this you'll find in lecture slides and in the study guide. But if we've got two vectors, say U1 like this and U2 like this, then we can always divide any vector, so this is U1 and that's U2, we can always divide this second vector into a component which is parallel to U1, so it goes out to here, and then a component which is perpendicular to U1, and that's the remainder here. So this is the component which is parallel is called the projection of U2 onto U1. Sorry about the small handwriting, but you should be able to figure this out from the lecture notes. And this one here is the orthogonal component. And we can see that just these three vectors form a triangle. And so this orthogonal component must be equal to U2 minus the projection of U2 onto U1. So it's equal to the total vector, take the parallel component. So we're just going to write that down straight away. And this generalizes when we've got three vectors to work out the perpendicular component to a previous set of orthonormal basis vectors. We just subtract away the projection of that vector onto each of those different basis vectors. Okay, so if we look at this, we will next evaluate an orthogonal vector. So we're going to call this V2. This is going to be a vector, the component of U2, which is orthogonal to U1. That's going to be equal to U2, take the projection of U2 onto U1. Now, I use a different formula for the projection of U2 onto U1. I think of it as, to work out the projection of U2 onto U1, I will need to work out the component, the magnitude of the component in the U1 direction, which I just get by the dot product of U2 with the unit vector in the same direction as W, as the same direction as U1, which is W1. And then I'm going to multiply that by, I should have called this, I'm very sorry, I don't know why I did this. I would usually call this W1 hat. Okay, so I'll change the notation back. Don't know why I wrote it that way. So unit vectors I'll typically write as a hat. Okay, so I've got U2.W1 hat that tells me the component of U2 in the U1 or alternatively the W1 direction, and then we multiply by the unit vector in that direction. You can also write this as U2 dot U1 times U1 over the magnitude of U1 squared. Okay, so that's an alternative method, but frankly I find this this one I can remember, this one I can't remember. So now I just need to evaluate these things. So I know what W1 hat is, I know what U2 is, so I'll just write them down. So U2 is equal to 0 minus 1, 1. I'm going to subtract away the dot product, which is just a number, of 0 minus 1, 1. Dot product of that with W1 hat, which is 1 on root 5, 2, 0, 1. And I'm going to multiply that by the W1 vector, which is 1 on root 5, 2, 0, 1. Okay, I'm going to simplify a little bit further, so I end up with 0 minus 1, 1. Now I can see I've got a 1 on root 5 and another 1 on root 5. That gives me an overall factor of 1 on 5, so I'm going to subtract 1 on 5. Then I've got the dot product of 0 minus 1, 1 with 2, 0, 1. That gives me 0 plus minus 0 times 2 plus 0 times minus 1 times 0 plus 1 times 1. And that's going to be multiplied by, that's the coefficient of the vector 2, 0, 1. So this is equal to, I'm going to write it just to avoid going on to another slide. This is equal to 0 minus 1, 1. I would be a bit annoyed if you actually did this in a test or an assignment. To tell you the truth, you should always write equals underneath each other if you can. So this is equal to 0 minus 1, 1. Take 1/5 times 2, 0, 1. So I'm going to write that as minus and I'll bring the 1/5 inside, so I've got 2/5, 0, 1/5, and so that's equal to 0 take 2/5 is minus 2/5, minus 1 take 0 is minus 1, 1 take 1/5 is 4/5. So I've worked out the component of U2 which is perpendicular to both U1 and also our first basis vector. It's perpendicular to W1 hat. So the next thing to do is we've got a second vector which is orthogonal to the first one. So V2 is orthogonal to W1, but it doesn't have unit magnitude. So we're going to evaluate V2, the magnitude of V2. So give me a sec, that is equal to, so it's 2/5, 1 4/5. So it's the square root of minus 2 squared plus 1 squared plus 4/5 squared. I'm going to put this all over a common denominator of 5 squared. So that's the square root of 4 plus, I'm putting everything over 25. So I had 4 squared over 5 squared, so 4 squared over 25, plus 1 squared, so that's 25 over 25, plus 16 over 25. So that's equal to, so 16 plus 25 is 41, plus 16 is 57. So I get the square root of 57 over the square root of 25, which is just 5. And so finally, our unit vector in our unit basis vector in our orthonormal basis is just equal to a vector in the same direction as V2, but normalized to have magnitude 1. So that's equal to, so 1 over V2, I just flip that, and I end up with 5 over square root of 57. Give me a sec. Aha, okay, no, I stuffed that up. Alright, it's not the square root of 57. It's actually equal to so I should have ended up with 4 over 25 plus 25 over 25 plus 16 over 25. So that is 29 plus 16, that's 45. So I've got the square root of 45 over 45. If I wanted to, I could simplify that down further. So I could write that as the square root of 9 times 5. And so I could simplify a little bit down by taking out yeah, I'm going to do that. No, I'll leave it the same because I noticed that that's what's included in the study guide. We could write square root of 45 is equal to the square root of 9 times 5, which is equal to 3 root 5. So we could write that the magnitude of V2 is equal to 3 root 5 over 5, and I can rewrite that if I multiply that by square root of 5 over square root of 5, and then I'll see that this is equal to 3 over square root of 5. It's just a little bit simpler. Okay, but I'll just leave it like it is. That's fine. So 1 over V2, I just flip the square root of 5, 45 and 5. I get 5 over square root of 45 times V2, and V2 was equal to minus 2/5 minus 1 4/5. And we're done. So W2 hat is the second orthonormal basis vector. So I could write, i.e., an orthonormal basis for V is just given by the set of the two vectors W1 hat, W2 hat, where those vectors are, where W1 hat and W2 hat are given above. We could use the notation which is given in the published solutions and say that V is equal to the span of W1 hat and W2 hat. So this is also true, but I would just say that the set of basis vectors is W1 hat, W2 hat, and we're done. Like I said, we could, if we wanted to go one step further, we could conceivably slightly rewrite these expressions. So for example, we could rewrite, take this factor of 5 and multiply that through the vector. So we could write this as 1 over square root of 45 times minus 2 minus 1, 4. But there are lots of different equivalent. So minus 2, 5 times minus 1 gives us minus 5, and then 5 times 4 over 5 gives us 4. So there are different equivalent expressions. As long as it's not too messy, then any such answer is perfectly acceptable.